February 12, 1945. Somewhere over the Philippine Sea, Lieutenant Hans Dortenmann pushed the throttle of his captured Chancevort F4U 1D Corsair forward, feeling 2,050 horsepower surge through the massive Pratt and Whitney R2800 double Wasp radial engine mounted ahead of his cockpit. The inverted gull wing configuration pitched upward as airspeed climbed through 370 miles per hour at 15,000 feet. Dortenmann, one of the Luftwaffe's most experienced test pilots with 38 confirmed victories over the eastern and western fronts, had flown nearly every German fighter type operational between 1940 and 1944. He had tested captured Soviet Yaks and Lavochkins, British Spitfires and Typhoons, and American Thunderbolts and Lightnings at Rechlin-Lärz Airfield, the Luftwaffe's primary testing facility in Mecklenburg. But nothing in his extensive combat experience or comprehensive testing background had prepared him for what he was experiencing in this moment. The Corsair accelerated with a brutal directness that felt less like conventional piston engine propulsion and more like something elemental and unstoppable. The massive four-bladed Hamilton Standard propeller, 13 feet and 4 inches in diameter, clawed through the air with authority that made the Focke-Wulf 190's BMW 801 radial feel civilized by comparison. Dortenmann banked hard left, pulling 4 Gs through a 60-degree climbing turn. The Corsair responded instantly, its control surfaces firm and responsive despite the high load factor. He rolled inverted, pulled through, and dove toward the mock target painted on the test range below. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. At 420 miles per hour in a 30-degree dive, the aircraft remained rock solid, stable, no vibration, no flutter, no hint of the control difficulties that plagued German fighters pushed beyond their design limits. Dortenmann leveled out at 5,000 feet and checked his notes strapped to his right thigh. Maximum speed at altitude exceeded 446 miles per hour. Rate of climb at sea level measured 4,020 feet per minute. Service ceiling reached 41,000 feet. Combat radius with full internal fuel stretched 395 miles. These numbers represented performance that no operational German fighter could match across the complete envelope. The Messerschmitt Bf 109 Gustav, the Luftwaffe's primary fighter through 1944, achieved 386 miles per hour at altitude, with a service ceiling of 39,000 feet and combat radius barely exceeding 200 miles with external tanks. The Focke-Wulf 190 Anton reached 408 miles per hour, but suffered at high altitude, where supercharger efficiency dropped and performance degraded rapidly above 25,000 feet. Even Germany's latest piston fighters, the Focke-Wulf 190 Dora with its inline Junkers Jumo 213 engine and the specialized Focke-Wulf TAR 152 high-altitude interceptor, could not match the Corsair's combination of speed, climb rate, and operational ceiling. The jet-powered Messerschmitt Me 262 possessed superior speed, but chronic engine reliability problems, limited operational availability, and crippling fuel shortages meant the revolutionary jet fighter existed more as a technological curiosity than an operational game-changer capable of influencing strategic outcomes. Dortenmann pushed the throttle to maximum continuous power and climbed toward 25,000 feet. The Corsair ascended smoothly, its two-stage supercharger maintaining manifold pressure as altitude increased. German fighters typically experienced significant power degradation above 20,000 feet. The Corsair maintained full power output well into the stratosphere. This was not simply superior engineering in one area, this was comprehensive technical excellence across every performance category that mattered in aerial combat. Speed determined who could choose when to engage and when to escape. Climb rate determined who reached advantageous altitude first. Service ceiling determined who could attack from above with energy advantage. Range determined who could escort bombers deep into enemy territory or conduct extended combat operations far from base. The Corsair possessed decisive advantages in every single category. Dortenmann understood immediately that German pilots facing this aircraft in combat operated under fundamental disadvantages that no amount of training, experience, or tactical skill could overcome. The captured Corsair he was flying represented just one aircraft from production runs that numbered in the thousands. American industrial capacity was producing these fighters at rates that defied German comprehension. Chance Vaught's Stratford, Connecticut plant, Goodyear's Akron, Ohio facility, and Brewster's Long Island factory together produced over 12,500 Corsairs between 1942 and 1945. Peak monthly production exceeded 400 aircraft. Germany's entire fighter production for 1944, including all Messerschmitt, Fokker-Wulf, and Heinkel types combined, totaled approximately 25,000 aircraft. The United States alone produced over 38,000 fighters in 1944, not counting bombers, transports, trainers, and reconnaissance aircraft. This disparity in industrial output meant that even if German fighters achieved favorable exchange ratios in combat, which they increasingly did not, the Allies could replace losses faster than Germany could inflict them, while simultaneously expanding operational capabilities and introducing improved models. The story of how the Corsair came to dominate Pacific skies and force German test pilots to confront overwhelming American technical and industrial superiority begins not with any single combat engagement, but with the systematic development of carrier-based fighters capable of competing with land-based opponents on equal or superior terms. In 1938, the United States Navy issued specification requests for a new carrier fighter to replace the aging Grumman F-3F biplane, then serving aboard American carriers. The requirements were demanding and reflected lessons learned from combat reports emerging from the Sino-Japanese War and the Spanish Civil War. The Navy wanted maximum speed achievable with available engine technology, excellent climb rate for rapid altitude gain during fleet defense, heavy armament capable of destroying enemy bombers with short firing passes, long range for extended patrols and escort missions, and compatibility with carrier operations including catapult launches and arrested landings. Chance Vought Aircraft Company, based in Stratford, Connecticut, submitted a radical design proposal that centered on the most powerful aircraft engine then available, the Pratt & Whitney R2800 Double Wasp, an 18-cylinder twin-row radial producing 1,850 horsepower at takeoff. The R2800 represented a breakthrough in piston engine design, combining high power output with relatively good fuel efficiency and mechanical reliability. But the massive engine created significant design challenges. The required propeller diameter for optimal efficiency exceeded 13 feet. Carrier-based fighters required substantial ground clearance for deck operations. Conventional landing gear long enough to provide adequate propeller clearance would be impossibly heavy and structurally weak. Vaught's chief designer, Rex Beisel, solved this problem with an NAR, inverted gull wing design that allowed short, strong landing gear while maintaining necessary propeller clearance. The wing geometry appeared unusual, almost awkward in static photographs, but provided multiple aerodynamic advantages. The inverted gull configuration allowed the landing gear to attach at the lowest point of the wing, where it could be shortest and strongest. The upward-angled outer wing panels reduced drag at the wing root junction where fuselage and wing met. The design also provided excellent low-speed handling characteristics crucial for carrier approaches and landings. Vought designated the prototype F4U and conducted first flight on May 29, 1940. Test pilot Lyman Bullard reported excellent performance despite some control sensitivity issues at high speed. Initial testing revealed the aircraft could exceed 400 miles per hour in level flight, making it one of the fastest fighters in the world at that time. The Navy was impressed, but identified numerous issues requiring correction before operational service. Cockpit visibility was poor due to the long nose and high cockpit position. Landing characteristics were challenging, with a tendency toward bounce on carrier decks. Control forces became heavy at high speed. The aircraft required extensive modifications through 1941 and 1942 before Navy acceptance. Production F4U models entered service in late 1942, initially with land-based marine squadrons rather than carrier units due to remaining concerns about deck landing characteristics. Marine Fighting Squadron 124, VMF 124, received the first operational Corsairs in September 1942 and deployed to Guadalcanal in February 1943. The squadron's combat debut proved the aircraft's potential, despite initial teething problems with maintenance and logistics in the primitive conditions of forward Pacific bases. First Lieutenant Kenneth Walsh, flying with VMF 124, achieved the first Corsair combat victory on February 14, 1943, shooting down a Japanese Mitsubishi A6M0 fighter during combat over Guadalcanal. Walsh would eventually claim 21 victories flying Corsairs, earning the Medal of Honor for actions on August 15 and 30, 1943. Marine pilots quickly discovered that while the Corsair could not match the Zero's legendary maneuverability at low speeds, it possessed overwhelming advantages in speed, dive performance, and high-altitude capability. American tactical doctrine emphasized these strengths through boom and zoom attacks, where Corsair pilots used superior speed and climb rate to attack from altitude, make a single high-speed firing pass, and then zoom climb back to altitude before the enemy could respond effectively. Japanese pilots, trained in dogfighting tactics that emphasized sustained turning combat, found themselves unable to counter these tactics. Zeros could turn inside Corsairs at low speed, but Corsair pilots simply refused to engage in turning fights. They attacked with speed advantage, shot, and climbed away before Japanese pilots could bring their maneuverability advantages to bear. This tactical approach, combined with the Corsair's rugged construction and heavy armament of 650 caliber machine guns with 400 rounds per gun, made it devastatingly effective in the Pacific theater. By mid-1943, Marine Corsair squadrons operating from Henderson Field on Guadalcanal and other forward bases were achieving remarkable success against Japanese air forces. The aircraft's range allowed extended combat patrols that could intercept Japanese raids well before they reached Allied positions. Its speed and climb rate meant Corsair pilots often held altitude advantage at initial engagement. Its firepower could destroy enemy aircraft with brief firing passes. Production accelerated through 1943 and 1944 as multiple manufacturers tooled up for Corsair production. Goodyear Aircraft Corporation produced the FG-1 variant with slight modifications to accommodate their production processes. Brewster Aeronautical Corporation produced the F3A variant, though Brewster's quality control problems and production delays eventually led to contract termination. By 1944, Corsair production reached scales that would have seemed impossible just 2 years earlier. Chance Vaught's Stratford plant employed over 13,000 workers, operating multiple shifts. The facility produced one complete Corsair every 2 hours at peak efficiency. Goodyear's Akron facility matched this pace. Monthly output from both plants combined exceeded 400 aircraft by late 1944. The logistical infrastructure required to support this production scale was itself remarkable. Pratt & Whitney's East Hartford, Connecticut factory produced R-2800 engines at rates exceeding 1,000 per month. Hamilton Standard in East Hartford manufactured the complex constant-speed propellers with hydraulic pitch control that gave the Corsair its excellent performance characteristics. Subcontractors across the United States produced thousands of individual components, from landing gear assemblies to gun sights to radio equipment. The entire supply chain operated with efficiency that reflected years of industrial development and organizational expertise. Raw materials flowed into factories, components moved through production lines, finished aircraft rolled out to acceptance test centers, and operational units received new fighters at rates sufficient to not just replace combat losses, but continuously expand force structure. Germany's fighter production, though substantial in absolute terms, operated under severe constraints that prevented comparable output quality and consistency. Strategic bombing disrupted production facilities and supply chains. Raw material shortages forced compromises in construction quality. Slave labor, while numerically significant, lacked the skill and motivation of properly trained workers. By late 1944, German fighter production faced catastrophic problems. Aircraft rolled off assembly lines but could not be delivered to units due to fuel shortages and transportation infrastructure collapse. Pilots completed abbreviated training programs but lacked the flight hours necessary for combat proficiency. Replacement aircraft arrived at operational units but could not be properly maintained due to spare parts, shortages, and overworked ground crews. The Corsair, meanwhile, represented not just an excellent fighter design, but also the culmination of American industrial might, trained workforce quality, secure supply chains, and effective logistics systems that together produced military capability at scales Germany could not match. Every Corsair that entered service carried with it the accumulated technical knowledge of Pratt and Whitney's engine designers, Chance Vaught's structural engineers, Hamilton Standard's propeller specialists, and thousands of skilled workers who transformed raw materials into combat aircraft through precision manufacturing processes. The aircraft's combat record reflected this comprehensive excellence. Marine Corsair squadrons in the Pacific achieved kill-to-loss ratios that demonstrated overwhelming superiority. VMF-2-14, the famous Black Sheep Squadron led by Major Gregory "Pappy" Boyington, claimed 94 enemy aircraft destroyed in 84 days of combat operations between September and December 1943. Boyington himself achieved 22 confirmed victories before being shot down and captured by Japanese forces on January 3, 1944. He survived captivity and received the Medal of Honor after the war. VMF-2-15, nicknamed the Fighting Corsairs, claimed 137 enemy aircraft destroyed during combat operations in the Solomon Islands campaign. First Lieutenant Robert Hansen of VMF-215 shot down 25 Japanese aircraft in 17 days of combat during January 1944 before being killed in action on February 3. He received the Medal of Honor posthumously. These individual achievements and unit successes reflected systematic American advantages in aircraft performance, pilot training, maintenance support, and operational logistics. Japanese forces fought with courage and determination, but faced opponents with superior equipment backed by industrial and training systems that could sustain combat operations indefinitely while continuously improving capabilities. The captured Corsair that Hans Dortenmann flew at Rechlin in early 1945 had arrived in Germany through circuitous routes that illustrated the complex intelligence-gathering operations both sides conducted. Throughout the war, German intelligence services maintained networks of agents and observers who reported on Allied aircraft development, production, and operational deployment. Luftwaffe reconnaissance units photographed Allied airfields and counted aircraft types to assess numerical strength and technological trends. Intelligence analysts compiled reports from combat pilots, interrogated captured airmen, and studied wreckage recovered from crash sites to build comprehensive pictures of enemy capabilities. The specific Corsair Dortenmann tested had been captured in Italy after an emergency landing behind German lines resulted in the pilot's capture and the aircraft's recovery with repairable damage. German salvage teams evaluated the wreck, determined restoration was possible, and transported it to Rechlin, where skilled technicians worked to return it to flying condition. The process required months of careful work. German mechanics had to understand American engineering practices, metric to imperial conversions, and maintenance procedures documented in technical manuals they struggled to interpret accurately. Replacement parts came from other wrecks or were fabricated at Rechlin's machine shops when original components were unavailable or damaged beyond repair. The R2800 engine presented particular challenges. This sophisticated power plant incorporated features German engines lacked, including a two-stage supercharger with intercooler for high-altitude performance and water injection for emergency power boost. German technicians studied the engine carefully, taking detailed measurements and creating technical drawings. They test-ran the engine on ground stands before reinstalling it in the airframe. They replaced damaged cylinders, repaired the complex reduction gear system that connected engine crankshaft to propeller shaft, and restored the intricate supercharger mechanism. Eventually, after extensive work, the Corsair was declared airworthy and ready for flight testing. Dortenmann received the assignment due to his extensive experience with captured Allied aircraft and his reputation as a careful, analytical test pilot who could provide useful tactical intelligence rather than just enthusiastic but vague impressions. His test program included systematic evaluation across the complete performance envelope. He conducted level speed runs at multiple altitudes to verify maximum velocity. He performed timed climbs to measure rate of climb at various altitudes and configurations. He tested ceiling by climbing until the aircraft could no longer maintain altitude. He evaluated handling characteristics through aerobatic maneuvers, simulated combat situations, and high-speed dives. He assessed control forces, control harmony, stall characteristics, and spin recovery. His written report, filed with Luftwaffe High Command, contained detailed performance data and tactical recommendations. The numbers told a sobering story. The Corsair outperformed every operational German fighter in nearly every measurable category. Its speed exceeded German types by 40 to 60 miles per hour, depending on altitude. Its climb rate was 30 to 50% better. Its service ceiling was 2,000 to 3,000 feet higher. Its range was double or triple that of German fighters. The tactical implications were stark and undeniable. German fighters could not catch Corsairs unless the American pilots chose to engage. German fighters could not escape from Corsairs if American pilots pressed attacks. German fighters could not match Corsairs in sustained combat at high altitude, where thin air degraded normally aspirated engine performance but barely affected the Corsair's sophisticated two-stage supercharged power plant. Dortenmann's report included recommendations for tactics German pilots might use to improve survival chances against Corsairs. Fight only when holding altitude advantage. Attack from above using speed built in the dive. Make a single firing pass and escape immediately. Never attempt sustained maneuvering combat. Never allow the Corsair to dictate engagement terms. These recommendations reflected professional assessment of a difficult tactical problem. But they could not change the fundamental reality that German pilots faced aircraft superior in performance and available in numbers that reflected industrial capacity Germany could never match. The Pratt and Whitney R2800 double Wasp engine that powered the Corsair represented 15 years of continuous development in radial engine design. Pratt and Whitney engineers had begun work on large displacement twin-row radials in the late 1920s, seeking to create power plants that could deliver substantially more horsepower than existing single-row designs without proportional increases in frontal area and drag. The twin-row configuration placed 18 cylinders in two staggered rings around a central crankcase, allowing compact packaging of substantial displacement. The R2000, 800's 2,800 cubic inch displacement, achieved through bore and stroke dimensions, carefully optimized for thermal efficiency and mechanical stress distribution, generated 1,850 horsepower at takeoff power settings using 100-octane fuel. Later variants with water injection and higher-grade fuels would produce over 2,000 horsepower. The engine's two-stage supercharger system maintained power output at high altitude, where naturally aspirated engines lost effectiveness. The first supercharger stage compressed incoming air, which then passed through an intercooler that reduced temperature before entering the second stage for additional compression. This sophisticated system allowed the R2800 to maintain sea-level power output up to approximately 19,000 feet, providing performance advantages that proved decisive in high-altitude combat. German engine designers understood supercharging principles and had developed capable systems for their own engines. The Daimler-Benz DB605 that powered the Messerschmitt Bf109, Gustav used a variable-speed supercharger that provided good high-altitude performance. The BMW 801 radial in the Focke-Wulf 190 featured a sophisticated turbo supercharger arrangement. But German engines could not match the R2800's combination of high-power output, altitude performance, mechanical reliability, and fuel efficiency. American metallurgy provided heat-resistant alloys that allowed higher operating temperatures and pressures. American manufacturing precision produced tighter tolerances and better quality control. American fuel quality, with octane ratings reaching 150 by late war, allowed higher compression ratios and boost pressures. The cumulative effect of these advantages meant American engines delivered more reliable power across broader operating envelopes while requiring less maintenance and proving more tolerant of combat damage and operational stress. German pilots who survived being shot down and captured often expressed amazement at the quality and abundance of American equipment they encountered as prisoners of war. The food was better and more plentiful. The medical care was comprehensive and professional. The facilities, even in temporary POW camps, reflected organizational capabilities and resource availability that seemed almost incomprehensible to men who had spent years fighting under conditions of increasing scarcity and deprivation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German fighter pilots who flew captured Allied aircraft at Rechlin experienced similar revelations about American engineering and industrial capabilities. The aircraft were not just fast or well-armed, they were comprehensively excellent across every dimension that mattered. Control systems were harmonious and well-balanced. Cockpit layouts were logical and ergonomic. Instruments were clear and easy to read. Visibility was generally good despite some exceptions like the Corsair's long nose. Manufacturing quality was evident in tight tolerances, smooth surface finishes, and attention to detail throughout the airframe. Perhaps most significantly, the aircraft were designed for ease of maintenance and repair under field conditions. Cowling panels opened easily to provide access to engines and systems. Major components could be removed and replaced quickly using standard tools. Technical manuals, though written in English, provided comprehensive documentation of systems and procedures. American aircraft reflected design philosophies that prioritized not just performance but also operational sustainability, recognizing that combat aircraft must be maintained by overworked ground crews under difficult conditions with limited resources and time. German aircraft, by contrast, often featured complex systems that required specialized tools and extensive training to service properly. The Messerschmitt Bf 109's narrow-track landing gear made ground handling difficult and contributed to numerous landing accidents. The Focke-Wulf 190's complex BMW 801 radial, while powerful and sophisticated, proved challenging to maintain in forward operating conditions. These design characteristics reflected different priorities and assumptions about how aircraft would be operated and supported in combat conditions. The Corsair's operational record in the Pacific theater demonstrated what happened when superior aircraft design met comprehensive logistical support and thorough pilot training. Marine and Navy Corsair squadrons achieved overall kill ratios exceeding 11-1, with some elite units reporting ratios above 20-1 during specific operational periods. These statistics reflected multiple factors working in combination. The aircraft's performance advantages allowed pilots to engage or disengage at will, fighting only when conditions favored success. American pilot training provided extensive flight hours and realistic combat preparation that built skills and confidence. Maintenance and logistics systems kept aircraft operational and properly supplied with fuel, ammunition, and spare parts. Marine pilots who transitioned from earlier fighters to the Corsair consistently reported that the new aircraft transformed their combat effectiveness. Captain Joseph Foss, a Marine ace who had achieved 26 victories flying the Grumman F4F Wildcat earlier in the war, later noted that pilots flying Corsairs possessed capabilities that would have seemed impossible in earlier fighters. The Corsair's speed meant pilots could catch Japanese aircraft that would have escaped slower fighters. Its climb rate meant pilots could gain altitude advantage quickly. Its firepower meant brief firing opportunities often resulted in kills rather than just damage. The aircraft's rugged construction proved critical for survival in combat conditions. The R-2800 engine could sustain significant battle damage and continue running. The airframe could absorb punishment that would have destroyed more fragile designs. Multiple Corsairs returned to base with damage so extensive that ground crews expressed amazement the aircraft had remained flyable. This damage tolerance reflected careful structural design, redundant systems, and robust construction that prioritized survivability alongside performance. Japanese fighter pilots facing Corsairs experienced the inverse of these advantages. Their Mitsubishi A-6M0 fighters, though legendarily maneuverable at low speeds, could not match Corsair speed, climb rate, dive performance, or high-altitude capability. Japanese pilots trained in traditional dogfighting tactics found themselves unable to force Corsair pilots into the close-range turning fights, where zero maneuverability might provide advantage. American pilots simply refused to fight on Japanese terms, instead using speed and altitude to dictate engagement conditions. Japanese industry struggled to produce fighters capable of countering Allied performance advantages. The Kawasaki Ki-61 Hien and Nakajima Ki-84 Hayate represented attempts to field fighters with better speed and altitude performance than the Zero. Both types showed promise but suffered from production difficulties, engine reliability problems, and insufficient numbers to influence strategic outcomes. By 1944, Japanese aircraft production faced catastrophic material shortages, increasingly untrained workers due to conscription of skilled personnel, and systematic destruction of factories by American bombing. The result was declining production quality even as quantitative output remained substantial. Aircraft rolled off assembly lines with improperly heat-treated components, substandard materials substituted for specified alloys, and manufacturing defects that reduced performance and reliability. Japanese pilots often flew aircraft that could not achieve their designed performance specifications due to production shortcuts and material compromises forced by resource scarcity. Japanese pilot training programs collapsed under similar pressures. Fuel shortages forced drastic reductions in training flight hours. Experienced instructor pilots were sent to combat units to replace losses, leaving training squadrons staffed by less capable instructors. Training aircraft wore out and could not be adequately maintained or replaced. By late 1944, Japanese pilots entered combat with perhaps 50 to 100 hours total flight time, compared to American pilots who typically accumulated 300 to 400 hours before combat deployment. This training differential proved decisive in combat. Experienced pilots could exploit their aircraft's capabilities fully, using tactical sophistication to maximize advantages and minimize vulnerabilities. Inexperienced pilots struggled with basic aircraft handling, had difficulty managing complex combat situations, and often made fatal mistakes under stress. The systematic destruction of experienced Japanese pilots through attrition meant that by 1945, Japanese air units consisted largely of poorly trained replacements, flying worn-out aircraft with inadequate maintenance support and insufficient fuel. Corsair squadrons facing these opponents achieved lopsided victory ratios that reflected overwhelming American advantages across every dimension of air combat capability. But individual Japanese pilots, when given capable aircraft and adequate training, could still prove dangerous opponents. Several Japanese aces achieved substantial victory totals despite facing superior Allied aircraft and numerical disadvantages. These exceptional individuals demonstrated that skill and courage retained value even against systematic disadvantages. Though they could not change strategic outcomes, the Corsair's service extended well beyond World War II, demonstrating the fundamental soundness of its design and the quality of its construction. During the Korean War, Marine Corsair squadrons flew close air support missions with devastating effectiveness against North Korean and Chinese forces. The aircraft's ability to carry substantial ordnance loads, combined with its rugged construction and good low-speed handling characteristics, made it ideal for ground attack work. Marine Corsairs delivered bombs, rockets, and napalm with precision that made them feared by enemy troops and valued by United Nations ground forces, who relied on their support. The Corsair's combat record in Korea added another chapter to its already impressive legacy. Marine squadrons flew over 64,000 combat sorties, destroying bridges, supply depots, artillery positions, and troop concentrations. The aircraft proved nearly as effective in the ground attack role as it had been as an air superiority fighter a decade earlier. Several Corsair pilots achieved ace status during the Korean War by shooting down North Korean aircraft, though such opportunities were rare given United Nations air superiority and the scarcity of enemy aircraft. Foreign air forces operated Corsairs through the 1950s and into the 1960s, testament to the aircraft's continued utility long after its initial combat debut. The French Navy used Corsairs extensively during the First Indochina War, flying ground attack missions against Viet Minh forces from carriers and land bases. French pilots praised the aircraft's reliability, heavy ordnance capacity, and ability to operate from primitive forward airstrips. During the Algerian War, French Corsairs continued flying combat missions well into the late 1950s. The Argentine Navy operated Corsairs from the carrier ARA Independencia and shore bases, maintaining the type in service until 1968. Argentine pilots valued the Corsair's robust construction and straightforward handling characteristics. The Honduran Air Force flew Corsairs until 1969, making Honduras one of the last military services to retire the type from active duty. The fact that Corsairs built in 1944 remained operationally effective 25 years later demonstrated exceptional engineering and manufacturing quality that produced not just high performance but long-term durability. For German test pilots like Hans Dortenmann, who flew captured Corsairs at Rechlin and understood what the aircraft represented, the experience was both professionally instructive and personally sobering. They recognized superior engineering when they encountered it. They understood that American designers had created an aircraft combining high performance with practical reliability and operational flexibility. They knew that German industry could not produce comparable aircraft in necessary numbers, even if designers developed equivalent designs. Most significantly, they understood that the war had moved beyond Germany's capacity to compete effectively in the technical and industrial dimensions that increasingly determined outcomes. Dortenmann's detailed test report on the captured Corsair circulated through Luftwaffe channels, reaching commanders and staff officers responsible for tactical planning and strategic assessment. The report's conclusions were professionally stated but strategically devastating. German fighters could not compete with Corsairs on equal terms across the performance envelope. Tactical recommendations might improve German pilot survival rates marginally, but could not overcome fundamental performance disadvantages. The numbers of Corsairs entering service, combined with other Allied fighter types of comparable capability, meant that German air forces faced quantitative and qualitative disadvantages that would only worsen as the war continued. Some Luftwaffe officers who read the report understood its implications immediately. The war was lost. Allied air superiority was absolute and irreversible. German forces could continue fighting, and individual pilots could achieve local successes through skill and courage, but strategic outcomes were no longer in doubt. Other officers refused to accept these conclusions, clinging to hopes that new technology, like jet fighters or miracle weapons, would somehow reverse Germany's deteriorating position. But the evidence accumulated relentlessly. Every captured Allied aircraft tested at Rechlin told the same story of American technical and industrial superiority. The admission by German pilots that they had never expected an aircraft with 2,000 horsepower was more than simple tactical intelligence or professional respect for enemy engineering achievement. It was recognition that the Allied powers, particularly the United States, possessed industrial capabilities and technical sophistication that Germany could not match. The Pratt and Whitney R2800 represented decades of development in piston engine design, advanced supercharging technology, sophisticated metallurgy, and precision manufacturing. American industry could produce these complex engines at rates exceeding 1,000 per month while maintaining quality standards that ensured reliability and long service life. Germany's BMW and Daimler-Benz piston engines, though well-designed and capable in absolute terms, could not match this combination of power, reliability, and production volume. The jet engines that powered the Messerschmitt Me 262 represented a technological leap forward, but they came too late, in too few numbers, with too many reliability problems, and required fuel that Germany no longer possessed in sufficient quantities. The Jumo 004 turbojets that powered the Me 262 suffered from short service lives, often failing after just 10 to 15 hours of operation. The turbine blades, made from inferior alloys due to Germany's shortage of heat-resistant materials like chromium and nickel, deteriorated rapidly under high temperatures and stresses. Allied intelligence officers who interrogated captured German pilots and examined recovered German aircraft came to understand the extent of Germany's material and industrial difficulties. German fighters increasingly featured ersatz materials and simplified construction techniques that reflected resource scarcity. Wooden components replaced aluminum parts, cheaper alloys substituted for specified materials. Manufacturing shortcuts reduced production time but also reduced quality and durability. These compromises were forced by Allied bombing of German industrial facilities, raw material shortages caused by naval blockade and loss of conquered territories, and the systematic destruction of Germany's transportation infrastructure. The final phase of the air war over Europe demonstrated what happened when one side possessed overwhelming advantages across every dimension of military power. Allied fighters dominated European skies, not through any single factor, but through cumulative effects of superior aircraft design, excellent pilot training, robust logistics, effective maintenance, secure supply chains, massive industrial production, and strategic positions that allowed sustained operations while enemy capabilities collapsed under multiple pressures. German and Japanese pilots who flew against Corsairs, Mustangs, Thunderbolts, Lightnings, and other Allied fighters in 1944 and 1945 faced tactical situations, offering few good options and many ways to die. They could engage and likely be shot down by faster, more powerful aircraft flown by well-trained pilots with numerical superiority. They could refuse combat and watch helplessly as Allied aircraft attacked ground targets unopposed. They could conserve fuel and limit operations, effectively ceding air superiority by default. None of these options led to victory. All reflected the fundamental reality that industrial warfare rewards the side that can produce better equipment in greater quantities, train personnel more thoroughly, sustain operations longer, and replace losses more quickly than the enemy can inflict them. The Corsair's 2,050 horsepower represented not just mechanical power, but industrial capability, technical knowledge, organizational competence, and accumulated expertise. Every one of those horses under the cowling embodied the work of Pratt and Whitney engineers who designed the engine, metallurgists who developed heat-resistant alloys capable of withstanding extreme temperatures and pressures, machinists who manufactured components to tolerances measured in thousandths of an inch, and assembly workers who fitted everything together with care that ensured reliability and long service life. The aircraft surrounding that massive engine represented similar accumulated expertise in aerodynamics, structures, systems integration, and manufacturing engineering. The inverted gull wing solved multiple problems simultaneously, while creating distinctive appearance that made the Corsair instantly recognizable. The hydraulic systems that operated landing gear, flaps, and tailhook functioned reliably despite combat damage and harsh operating conditions. The electrical systems powered radios, instruments, and gun charging mechanisms through carefully designed circuits with appropriate redundancy. Every system reflected thoughtful engineering that balanced performance requirements against weight constraints, manufacturing practicality, and maintenance accessibility. The pilot who flew that aircraft represented training programs that provided hundreds of flight hours, realistic combat preparation, thorough grounding in tactics and techniques, and continuing education throughout combat deployments. American pilot training began with careful selection processes that identified candidates with appropriate aptitude and motivation. Initial training provided comprehensive instruction in basic flying skills, navigation, and aircraft systems. Advanced training introduced combat tactics, gunnery, formation flying, and emergency procedures. Operational training units provided final preparation using aircraft identical to those flown in combat, often with instruction from experienced combat pilots rotated back to training duties. This systematic approach produced pilots who entered combat with confidence born from competence rather than bravado or ideology. They understood their aircraft's capabilities and limitations. They knew how to exploit performance advantages while avoiding situations that favored enemy strengths. They could execute complex tactical maneuvers under stress while maintaining situational awareness and making good decisions rapidly. The contrast with German and Japanese pilot training by late war was stark and strategically decisive. The logistical systems that supported Corsair operations ensured aircraft had fuel, ammunition, spare parts, and maintenance support necessary to generate sorties consistently and sustain operations indefinitely. American logistics, though often underappreciated compared to more dramatic aspects of military operations, represented organizational capabilities that proved strategically decisive. Supply ships delivered fuel, ammunition, and spare parts to forward bases on regular schedules. Depot maintenance facilities performed major overhauls and repairs that exceeded capabilities of squadron maintenance sections. Technical representatives from manufacturers provided expertise for complex problems. The entire system operated with efficiency that kept aircraft operationally ready at rates German forces could only envy. When Hans Dortenmann landed the captured Corsair at Rechlin after his comprehensive test flight, he taxied to the designated parking area, shut down the massive R2800 engine, and sat quietly in the cockpit for several moments before climbing down. Ground crew personnel who had watched the flight gathered around, asking questions about the aircraft's performance and handling. Dortenmann answered briefly, noting the Corsair's impressive capabilities while maintaining the professional detachment expected of test pilots, providing objective evaluations rather than emotional reactions. But privately, Dortenmann understood that he had just flown an aircraft representing everything Germany lacked in 1945. Not merely superior performance in quantifiable categories like speed and climb rate, but the industrial depth, technical sophistication, organizational capability, and systematic excellence that produced such aircraft by thousands while maintaining quality and reliability that ensured operational effectiveness. His detailed written report to Luftwaffe High Command documented the Corsair's capabilities with professional thoroughness, including precise performance measurements, handling characteristics across the flight envelope, tactical recommendations for German pilots who might face Corsairs in combat, and technical observations about design features and engineering solutions. But the report's subtext was clear to anyone who read carefully and understood strategic context. Germany had lost the air war comprehensively and irreversibly. The evidence sat on Rechlin's runway, painted in captured American markings, powered by an engine representing technical and industrial advantages Germany could not match. The 2,050 horsepower of the R2800 double Wasp, the 446 miles per hour maximum speed, the 41,000-foot service ceiling, the 4,000 feet per minute climb rate, the nearly 400-mile combat radius. These numbers told a story of systematic American advantages across every dimension of aerial warfare capability. The admission by German pilots that they had never expected. Such power represented more than tactical intelligence or professional acknowledgement of enemy engineering achievement. It was recognition that the war had been decided by factors extending far beyond individual courage or tactical skill, though both remained admirable and respected. Industrial capacity, resource availability, technical expertise, organizational competence, and strategic position determined outcomes in modern warfare. Germany had lost advantages in all these areas through combination of Allied superiority and self-inflicted wounds caused by Nazi ideology, strategic miscalculations, and moral corruption that undermined effectiveness while guaranteeing eventual defeat. The Corsair represented victory written in horsepower and high-octane fuel, in precision manufacturing and rigorous quality control, in comprehensive training programs and sophisticated logistics systems, in secure supply chains and protected industrial bases. It was an aircraft that could be produced by thousands, flown by well-trained pilots who understood how to exploit its capabilities, maintained by skilled ground crews with adequate tools and spare parts, and sustained by logistics networks that never failed to deliver fuel, ammunition, and everything else required for continued operations. Against such systematic advantages, individual courage and tactical skill though admirable and sometimes effective at tactical level, proved strategically insufficient to influence outcomes. The skies over Europe and the Pacific belonged to those who could produce not just more aircraft, but decisively better aircraft, backed by everything necessary to use them effectively and sustain operations indefinitely against opponents whose capabilities deteriorated under cumulative pressures they could not overcome. The final months of World War II witnessed the complete collapse of German and Japanese air power under relentless Allied pressure. Fuel shortages grounded aircraft that might otherwise have flown. Pilot losses could not be replaced with adequately trained personnel. Industrial production continued, but could not keep pace with destruction rates. Logistics systems broke down under bombing and infrastructure collapse. The end came not through any single catastrophic defeat, but through cumulative exhaustion that rendered continued resistance futile. For the men who had fought in the air war, on both sides, the experience left lasting impressions that shaped their understanding of warfare, technology, and human conflict. Allied pilots who had flown Corsairs and other advanced fighters remembered the confidence that came from knowing their aircraft were superior and their support systems were reliable. German and Japanese pilots, who had survived the war, remembered the desperation of fighting against overwhelming odds with inadequate equipment and insufficient support. Both groups understood that modern warfare had become industrial contest, where victory belonged to those who could outproduce, out-innovate, and outlast their opponents. The Corsair's legacy extended beyond its impressive combat record and long service life to represent a particular moment in aviation history when piston engine fighter design reached maturity through systematic refinement of established principles. The aircraft combined proven technologies like radial engines, conventional structures, and simple systems into a package that worked reliably under demanding conditions. It represented evolutionary excellence rather than revolutionary innovation, the culmination of incremental improvements rather than radical departure from established practices. This evolutionary approach proved strategically superior to revolutionary gambles like German jet fighters that promised performance breakthroughs but suffered from immaturity, unreliability, and resource demands that could not be satisfied. The Corsair worked consistently because its technologies were mature and its engineering was sound. It could be produced in quantity because its manufacturing requirements matched available capabilities. It could be maintained in forward conditions because its systems were relatively simple and its design accommodated field repairs. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.